Hello and welcome to Tutorial 4 of MH1801 Calculus for the Sciences. Today we're going to start looking at second order differential equations. In this tutorial we have an additional condition. The differential equation should be homogeneous as well. What does this mean? It means that the left-hand side is precisely the same thing as if we are dealing with a linear differential equation. That's why it is also linear. But moreover, g of x, in this special case, is just 0. So the only difference is that the right-hand side is constant. It is 0. This tutorial also brings us to consider two kinds of problems associated to linear and homogeneous differential equations. These are initial value problems and boundary value problems. When we deal with initial value problems, what we need is to look at a single point x0, and for this point we need two pieces of information. The first piece is what is the value that the solution y takes at x0. That will give us, say, y0. And the second condition is we need to know what value does the derivative y prime, our dy dx, what value does it take at x0? Let us say that the value taken is y1. We need to have, for an initial value problem, information about the derivative dy dx. For such cases, it turns out that we always have a solution. There is always going to be a solution to initial value problems. The other kind of problem is called a boundary value problem. In this case, we don't consider the derivative dy dx. What we do is that we specify 2 points, 2 different points, x1 and x2. And we ask, what values does the solution, if it exists, take at these 2 points? What is y at x1? And what is y at x2? Say the values are given by y1 and y2. This constitutes our boundary value problem. But we are going to note that there may not always be a solution to a boundary value problem. You will see in one of the questions of this tutorial that there is a differential equation that is linear and homogeneous with a boundary value problem but doesn't have a solution to it. There's no solution curve to that particular question. We are not going to work with general second order differential equations that are linear and homogeneous. We're going to focus on a very special type of these kinds of equations. They are of this form. The functions P2, P1, and P0, they are all constants. P2 is constant with value A, but we specify that A should not be 0. P1 is going to be constant with value B, and P0 equals to C, yet another constant. And because the right hand side is 0, you can see this is indeed a linear and homogeneous differential equation of the second order. We want to study these equations. How can we solve them? This is the approach that we shall use. The first thing that we do is to develop a key theorem which tells us a general method for solving differential equations of this special form. The first thing that we need is the characteristic equation of our differential equation, which we shall call star. What is the characteristic equation? We are going to take the coefficients of our differential equation and put them as the coefficients of a quadratic polynomial, a times lambda squared, which corresponds to the second order derivative, plus b lambda, and lambda corresponds to the first order derivative, plus c, and 1, c times 1 corresponds to the 0th order derivative. This is our characteristic equation, and using basic principles, we know how to solve this characteristic equation for the roots. With that, we come to the key theorem. Let us suppose that we have a second order linear and homogeneous differential equation of the special type derivatives and constant coefficients equals to 0 with characteristic equation, so that we can find the roots. Let us call them lambda 1 and lambda 2. From the characteristic equation, we are able to determine completely what the solution to this differential equation looks like. Then we consider the nature of the two roots lambda 1 and lambda 2. Case number 1. If it is true that both lambda 1 and lambda 2 are real numbers and both roots are not equal to each other. Then the general solution to our differential equation star is of this form: y equals to c1 times exponential to the power of lambda 1 times x. So lambda 1 is the first root, plus c2 times exponential to the power of lambda 2 times x, where lambda 2 is the second root. c1 and c2 are just real constants. They are arbitrary constants, allowed to take any real number of our choice. This is the first case. In the second case, we will have the lambda 1 and lambda 2 equal to each other. They are the same root. Let us also say it is a real number. Then the general solution in this case is given by this formula: y equals to c1 times exponential to the lambda x plus c2 times x times e to the lambda x. This is the general solution in this particular case. The final case is when both roots are complex numbers. Note that if lambda 1 equals to alpha plus beta I as a complex number, here I is taken as our square root of -1, then the other root, it is well known, must be the conjugate of lambda 1. In other words, the real part, alpha, stays the same, but the imaginary part, beta, is minus beta in the conjugate. Lambda 2, therefore, is the conjugate of lambda 1, so it must take this particular complex number. If this is so, then the general solution to our differential equation is given by this form: y equals to exponential to the power alpha times x. Alpha is the real part, times c1 times cosine of beta x. Beta is the imaginary part of lambda 1, plus c2 times sine of beta x. This is the general solution in the case where we have two complex roots. If both roots are complex numbers, they are conjugate, and this is how we determine the general solution, using the real and imaginary parts of the roots. So, with this key theorem, once we know what the roots of our characteristic equation are, immediately we can tell what the solution must be to a differential equation. We just need to understand whether the roots are real or complex. If they are real, are they equal to each other or are they not equal to each other? This entire tutorial is essentially about applying this key theorem to solve for the general solution. And with that, we shall proceed to use it to solve all the other questions.